Hey there, it's Jason from Codemanship with a rather shocking video diary entry today. I want to talk about modular design principles. I posted a tweet on the Codemanship Twitter account a couple of days ago that generated quite a lot of, shall we say, interest and a little bit of heat. And I followed that up with a blog post. I thought I'd follow the blog post up with a little video just to sort of go into a bit more detail about what I've been talking about. So I've been training and coaching developers in software design principles for many years now. And for much of that time, I was using the solid principles as a basis for talking about sort of modular design. But I found solid difficult to work with as a trainer, as a sort of explanatory tool, for three reasons. One is, well, that usually referred to as class design principles. And this is slightly exclusionary language. So many times on training courses in the past few years, we've had, for example, JavaScript developers who do functional programming, or what they believe is functional programming. And they say, well, these principles don't apply to us because we're not doing object-oriented design. They certainly do, but you need to translate. That makes life a little harder. So they're slightly exclusionary. They kind of got that OO feel to them, and that's understandable because they kind of date from a time when objects ruled the world. So OO programming was the dominant paradigm in the mid-1990s when those first papers on solid started to appear. So we can kind of forgive solid for that, but maybe the terminology does need updating slightly. It's not just talking about classes. The other problem I have with solid is that it's only 4/5 relevant to me these days. There's one letter in solid in particular, one of the principles that I think technology has caught up with us. I think things have moved on, and we'll explain that now. So one of the letters I find I have to explain why you don't really need to worry about that to many programmers, not to all programmers as we'll see, but to many programmers. And then finally, the main problem I have with solid is it's complicated. It is difficult to understand. You have to explain it multiple times. And there are even people out there I've seen who teach solid who don't seem to have understood the principles themselves. And I can kind of forgive them that, as we'll see when we get to the D in solid. They're not entirely intuitive. I think there's a little bit of what Richard Dawkins refers to as conservation of difficulty going on here, that actually the concepts are relatively simple, but they've been explained in a way that makes them sound much more sophisticated than they really are. And that puts people off, and it's a barrier to learning. So I've created my own kind of reduced set of modular design principles that I've had a lot more success with. And when I say success, it's been easier to teach, and the code that results from that tends to be more modular. They tend to get it more easily. And I'm a pragmatist in that sense, so I tend to measure it in terms of the end result. And if the end result is code that is more modular, has better separation of concerns, and et cetera, and is easier to test and all that good stuff, then I'm happy that it's done its job. So we'll get to my new shocking acronym soon, but let's talk about the mnemonic solid. So the S in solid stands for single responsibility. That is, the way it's explained is that classes should have one reason to change. So if we find we have a class where one part of the class is changing at different times for different reasons, maybe we can split them apart so we can change them and recompile them and retest them and re-release them independently of each other. That was the original thinking. And that is very good thinking. That is a very good rationale for designing modules. But I also think it's not the main reason. So when I talk about single responsibility, I talk about separation of concerns in terms of, let's think of, for example, your modular hi-fi, a modular hi-fi versus an integrated hi-fi. With a modular hi-fi, we have many more choices about how our hi-fi system can be composed. So we can compose many more systems out of those pieces. One of the exemplars of this in programming is Unix pipes, where you've got all these different Unix programs, each of which just does one job, and you can chain them together to do all sorts of extraordinary things. You get a lot more flexibility if each of the parts do only one job. So for me, single responsibility really is about composability, greater composability, than it is about separating areas of change. But that that is a valid reason for doing it as well. So we keep the S in solid. That's very important. Separation of concerns is a fundamental underlying principle of modular programming. Now, here's one that's problematic, the open-closed principle, that classes should be open to extension, closed to modification. So the thinking here is that it takes time to rebuild and retest and re-release modules. And if a module is working, we'd quite like to leave it that way so that the clients of that module can just carry on doing what they're doing and they don't have to be changed or rewritten or recompiled or retested. So in 1995, when the papers and writing on Solid was first starting to appear here in the UK, that was very valid. That was a real concern. Working in C++, for example, if I needed to compile the code, I would go away and have a break. It would take quite a long time. And as for testing the code, well, we used to run our tests overnight, and we thought that was advanced. The computers we were working on back then were about 1,000 times slower than the computers I'm working on today. So we throw a lot more hardware at the problem now, and that means that building and testing our code happens orders of magnitude faster, and therefore recompiling and retesting is not the big deal it used to be. At least it isn't if your tests run fast, and that's why it's important that your code is modular, so that it's more easy to unit test. So it's kind of a self-fulfilling prophecy here. The more modular your code is, the faster your tests can run, the less of a problem it is if you then need to recompile and retest stuff. But basically, the hardware moved on, technology caught up. And so the O in Solid, I have to explain to most programmers, you don't really need to worry about that so much. Unless you're working in certain programming languages where you have to redesign the code specifically to be more open to extension. So I am thinking here of languages like C++ and C#, for example, where the code, it has to be designed in a certain way, which is that things need to be more abstract. You're programming to interfaces explicitly a lot more. So there is some validity there for some of those kinds of statically typed languages where you would have to write the code differently in order to make it more open to extension. But if you're working in JavaScript or Python or Ruby or any of those languages, it's really not a problem. So the O in Solid it needs explaining, but as Kevin Henney has pointed out, quite rightly I think, it's more of a language design principle than a software design principle, that programming languages should be designed so that modules are open to extension by default. But in terms of modifying them, it's really not a big deal anymore. Really not a big deal, because we can recompile and retest code very, very quickly. Now, the L in Solid stands for Liskov Substitution, named after the computer scientist Barbara Liskov, and it's the only letter in Solid that has someone's name in it. And that's really about contracts. So I think the way it's stated is that something like an instance of any class can be substituted with an instance of any of its subclasses. But really, again, there's that word class that kind of puts people up. People go, oh, well, this is an object-oriented design principle. Well, now let's reframe that and talk about a function. Let's say that we've written some code that calls a function, and that function has a certain signature. Let's say we want to replace the implementation of that function with a different implementation that has the same signature. It looks the same from the outside. What the Liskov substitution principle is basically saying is that both that new implementation needs to obey the same contract as the original, so that we don't break the client code. So that's really what the L in Solid is all about. It's about contracts, not breaking contracts. The interface segregation principle, the I in Solid, states that classes should present client-specific interfaces. That is, interfaces should only expose the features that a client is using. And again, this is a language-specific thing. That's a big deal if you're working in C++, for example. It really isn't a big deal if you're working in JavaScript. In JavaScript, anything goes. If it looks like a duck and quacks like a duck, it's a duck. But in languages that, for example, enforce binary compatibility of types, if we just recompile an interface, then anything that depends on that interface needs to be recompiled and retested, etc. as well. So we're kind of in language-specific territory here. But I also think the interface segregation principle, which is a very valid principle, is coming at it from the wrong end. It's explaining it backwards. I think what's important here is from whose point of view are interfaces designed? Who are interfaces for? I see so many developers when it comes to designing interfaces and APIs, for example, talking about what services should this module provide. And that's coming at it from the wrong angle. The important question is, what services does this client require from that object or from that module? So come at it from the client's point of view, and you're likely to end up with interfaces that are client-specific because they were designed from that point of view. So a valid principle, in terms of the way that it's explained, it's language-specific, but I think more generally, if you approach it the other way around, which is you say, no, interfaces should be designed from the client's point of view, then you end up with something that's a more useful principle and a more generally applicable principle, I think. And finally, the big tamale, the D in solid, dependency inversion. Now here we go. High-level modules should not depend on low-level modules. Both should depend upon abstractions. Abstractions should not depend on details. Details should depend upon abstractions. Price of shares can go down as well as up. Small print, blah, 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 blah. Now, the D in solid is widely misunderstood, and it really doesn't surprise me, and I can't blame people for not understanding it because it is not very well explained. There's a much easier way of saying it, which is that dependencies should be swappable. If you've got a module that uses another module, it shouldn't depend directly on its implementation. It should depend on some kind of abstraction so that we can swap in a different implementation. For example, for stubbing and mocking, but for many other reasons as well, to swap a SQL Server database backend with an Oracle database backend. Very importantly, without having to rewrite the client code. The client is none the wiser. Because it all looks the same from the outside. And that's kind of what the O and the L and the D and the solid are all about. They're all about swappability, that when we're changing our system, we're doing it as much as we can by swapping in new implementations or by extending implementations rather than rewriting existing implementations. So that swappability is very, very important. But again, it's much more useful when you look at it from the client's point of view. The client's point of view. It's about not having to, it's about not breaking the client code, really, about localizing the impact of making that change to one module, and everything behind that module is hidden from the client. And talking of hidden from the client, another problem I have with solid is there's something very important missing. It might be implied, depending on what sort of lengths you're prepared to go to justify it. But as far as I'm concerned, and from years of experience applying solid principles and teaching them, it misses one of the most important sort of planks, foundations of good modular design, which is that modules should not expose their inner workings, that clients should not be exposed to the details of how that module does its job. So, for example, internal data, what data does it use? Dependencies, what dependencies does it have? Who else is it talking to? The client doesn't need to know or shouldn't need to know. The less the client code knows, the better for the client. The less likely it is the client's going to end up having to change because we've had to change one of those internal details. So this is really about coupling and cohesion of modules. And cohesion is kind of implied by single responsibility in the sense that, well, it has to have everything it needs, but it's not explicitly mentioned. And I think that's a big oversight because it often does need explicitly mentioning. So when I was teaching solid, I had to add this idea of encapsulation, of hiding internal workings, hiding data, for example, to make it more complete. So there was a lot to remember. Parts of it were difficult to understand, difficult to take in. There's a lot of words, a lot of syllables, and generally speaking, when there are lots of words and lots of syllables, and when parts of it maybe are not as applicable to what you're doing as other parts, and when it's described as being object-oriented, when really it's not object-oriented, it could just as well be about web services or about functions, then I feel, well, it really needed simplifying and making more widely applicable, ideally universally applicable. So I came up with my own acronym, which I now am beginning to teach. It's been recently unveiled, and here we go. So let's talk about SHOC. SHOC without a K. Yes, we'll get to that. SHOC without a K. Modular design principles. The first thing I've done is ditch the word class or ditch the word object. And so, no, this is about modules. So this would apply whether you were working in C# or JavaScript or Python or F# or Scala or Clojure or COBOL or Fortran. It doesn't matter as long as it supports modular programming. So the first thing we've done is we've made it more inclusive. And there are only 4 letters, and they represent words that are shorter. So let's get to those words. First of all, the S in SHOC, modules should be swappable. There you go. There's the O and the L and the D of solid explained in one word. Modules should be swappable. So if I'm using a module that talks to a database, I should be able to swap it with a different module, a different implementation that talks to maybe a different kind of database without having to rewrite any of the client code. And we'll take a look at how we can achieve that, for example, in Java a bit later. So S in SHOC, swappable modules. The H in SHOC, modules should hide their internal workings. So data, for example, if it's using data, then the client shouldn't need to see that data really. How is it doing it? So the example I've used in training is if you're calculating the area of a room for a fitted carpet, and it begins with the client knowing that a room has a width and a length, there's a getter and a setter, and it gets the width and the length and multiplies them together. And I go, but what if it's an L-shaped room? What if it's a circular room? What if it's a triangular room? How do we hide the details of how the room area is being calculated? We hide that data. We say, well, you don't need to know that it has a width and a length. You just need to know that it has an area. So the less the client knows, the better. But it's not just about the data. It's also, for example, you might have internal functions, helper functions, or internal classes or other modules. And you may have other dependencies, other modules that are being used in the work that this client is asking for that it doesn't need to know about. So all of those things, data, helper functions, helper classes, dependencies, they're all hidden from the client. The less the client knows, the better. So that's all what we mean by encapsulation there. So that's the S and the H of SHOC. What about the O? Well, here's a very important one. Modules should only do one job. For all the reasons we've just described, modules should only do one job. So you get much greater separation of concerns. You get much better composability of systems, testability of systems, all those things. So that's like always the first step, is to break stuff up into modules that are only each doing one job, and implied from that have one reason to change. So they kind of go hand in hand. And then finally, the C in SHOC, client-driven interfaces. So not necessarily client-specific, because I think that's coming at it from the wrong angle. Interfaces that were designed from the client's point of view. Not what services does this module provide, but what services does this client need that module to provide. And then we design the interface in order for those interactions to take place, specifically from that point of view. So we're talking about designing from the outside in here. So this all fits into outside in test-driven development. So there you go, that's SHOC without a K. Modules should be swappable, they should hide their internal workings, they should do one job, and they should have client-driven interfaces. And that would be just as true if you were working in Fortran or COBOL as if you were working in C# or Java or Python or any of those languages. So not object-oriented or functional or service-oriented or any of those paradigms, just modular. And that should come as no surprise, because it is built on basic foundations of modular programming that date back to the late 60s and early 1970s. So we talk about modules being interchangeable, about modules hiding their, well, typically we talk about information hiding, but I've generalized that a little bit. Said no, it hides how it does its job from the client, basically. One job, so we're talking here about separation of concerns. That was a phrase that was used very early on. And we're kind of adding client-driven interfaces. That's a more recent innovation in the way that we look at modules and the way that we look at software, but it's still universally applicable. It would apply just as much if you were designing electronic data interchange interfaces for a COBOL mainframe system. You design those interfaces from the outside, from the client's point of view, and then you end up with interfaces that include what the client needs and usually nothing else. So let's take a look at a Java example. Hopefully, yep, that's always good to know. Sorry, I started opening IntelliJ as I started this video. So I'm going to take a look at my Guitar Shack example, and we'll take a look at some of these modules So here's the outermost module of my Guitar Shack system. This is a system that listens for sales of products in a guitar shop. And when a sale takes a product stock to below a sort of minimum level, it then triggers an alert to the manager to reorder more stock for that product. So a very simple idea. And this stock monitor object here, its job is to listen for these sales. So we've got a product sold method here. We tell it which product we sold, how many we sold of that. And let's start with the S in SHOC. Its dependencies, the other modules, alert, warehouse, and reorder level. They're all being dependency injected into the constructor. And if we take a look, they're all interfaces, basically. So it'd be very, very easy to swap one implementation of alert, the thing that sends the alerts, with a different implementation. And indeed, in our test, if we take a look in our stock monitor test, that's exactly what we've done there. So our alert is a mock object. But we've also stubbed other things. So the thing that's supposed to calculate the reorder level, the minimum stock for that particular product, we faked that with a stub that just returns a hard-coded number. The thing that returns the information about the product at stock level, the delivery lead time, and so on and so forth, we fake that with a stub. And the reason we can fake it is because those modules are swappable. And indeed, all of the modules in this system are swappable by dependency injection. So we're ticking the S part of SHOC pretty strongly in this code. And it should be no surprise that we are, because we approached it from the outside in, writing failing tests and stubbing and mocking other parts of the design, so that we could solve one problem at a time. That's a very important point to make there. So if we look all the way down the call stack, all of the dependencies, all the modules are swappable by dependency injection. Now, hiding the internal workings. So if we take a look, for example, at, we've got this this warehouse interface here, and we wanted to look at the implementation of that. Oh, no, let's look in there. So we go and look for the thing that fetches the product data from the warehouse. There we go. The first thing to note is that our client, Stock Monitor, knows nothing about this implementation. So it doesn't know about its constructor, for example. It doesn't know that it needs a network client in order to function. That detail is hidden from it. The detail of how it does its work, this URL, for example, which probably shouldn't be in this code, is hidden. All these things are hidden, basically, from the client. The client does not need to know how the product information is being fetched from the warehouse. That's not the client's problem. So we get proper separation of concerns. And again, as we look through the call stack, so we look at this client interface, for example, that's also a swappable module. We can look to see under the net package here, we've got an implementation there of a REST client. Again, the details of how that works are hidden from product data. Product data does not know that it's a REST client because it's swappable. It's just an interface. It does not know that it requires a network connection. It does not know that it requires something that can build HTTP requests. It does not know how it works or any of this stuff. So all of that is hidden from those internal workings, are hidden behind that interface for the client from product data, and all of the detail about product data, how that works, is hidden from Stock Monitor behind the warehouse interface. So we're hiding here. We're hiding here. All that information is being hidden. So we're ticking the H of SHOC. We're hiding how these modules are working, their inner workings. So each module knows as little as possible about the rest of the system or about the internals of the modules that it's using. And again, that should come as no surprise because we faked it until we make it. So we only defined the interfaces first. So the detail of what goes behind that interface, that's somebody else's problem. So proper separation of concerns. Modules should only do one job. Again, we go through these modules that most of them have only got one method that actually does any work at all. So for the most part, I would say these modules are only doing one thing. That builds a web request, that executes an HTTP request to a REST web service, that connects to the web, and so on and so forth. So they're each doing, for the most part, one simple job. So we look at sales data. That's maybe this, yeah, this one's, there's a bunch of date stuff going on here. So I would get around to refactoring it and saying, well, let's pull all that date calculating stuff out of here so that this isn't having to do all of that. It's just deciding which dates to use instead. So we've got a bunch of objects here that are really only doing one job. That just does an average calculation and so on and so forth. So each module only does one job. tick. So that's the show so far of SHOC. And finally, another self-fulfilling prophecy, client-driven interfaces. Now, because of the way that we're approaching this, stubbing and mocking and working outwards from the outside in, that means that we have been defining the interface, for example, for alert and for reorder level and for warehouse. Those were designed from stock monitor's point of view. What does stock monitor need from these objects, from these modules? So yeah, we're definitely ticking that box very, very strongly. If we look at our interfaces, we look at warehouse, for example, only one method. It's only got what stock monitor needs. We look at recent sales, only one method. Sales rate, only one method. Client. So this is partly a side effect of each module and doing one job, but it also very strongly a side effect of those modules being designed from the client's point of view. Well, it only needs to ask it to do this. So our interfaces are 100% client driven because we use stubs and mocks to design them. We design them from the outside in this test driven way. So that is SHOC. SHOC, S-H-O-C, without a K. Now, I'm just going to finish by saying it's been quite fun watching people desperately try to sort of shoehorn a K onto the end of this, come up with, oh, well, K could stand for knowledge, or K could stand for whatever they think it could stand for, or just misspell things. K could stand for control with a K. And it has been fun to watch that, but I wanted to stay away from just adding things arbitrarily. I don't think it helps. I think SHOC is probably memorable enough. It's certainly a hell of a lot simpler than solid and easier to remember. It is deliberately widely applicable, possibly universally applicable to any programming languages that support modularity. It's specifically not object-oriented. It would apply just as much as we were talking about modules with functions or programs in COBOL, or however your code is organized. We can achieve very similar things. So there you go. There are SHOC without a K, SHOC modular design principles. This is the way that I'm going to be teaching it from now on. So far, it's been pretty successful. And when I say successful, successful in terms of the end result. Does it make a difference to people's code? Is people's code more modular as a result of applying SHOC principles? And the answer so far has been yes. A lot less confusion, a lot less scratching of heads with SHOC than I've found with solid. So I'm going to be moving forward with solid. SHOC, I'm not saying ditch solid. I'm not saying put SHOC on your CV. That's not my intention at all. This is not it's not my goal here to create a brand or anything like this. I'm just looking as a trainer and a coach for a simpler way and a more inclusive way and a more pragmatic way of explaining these principles. And I'm looking to bring it back to the original principles of modular programming from the late 60s and early 70s, so that we can include Fortran and COBOL and Pascal and all these other languages as well, so that people don't feel that they don't apply to them, or they don't feel left out, or they don't see how it applies to them. Okay, so there you go. SHOC design principles. Shocking, I know. Hope you're staying safe. Hope you're doing well. Light at the end of the tunnel, although the light seems to get further and further away every week. But this will be over soon, and we can all get back to being miserable in offices again. So until then, and until the next video diary, take care and stay shocking.